All right, so you start with this. Again, it's a Lilic star material here, treated with an aldehyde because, of course, the Wittig is used to convert aldehydes and ketones into alkenes, right? You can see the phosphine source right here, either triphenylphosphine or tributylphosphine, it doesn't matter. You one equivalent or 1 mole, like so the mole to mole ratio of everything is going to be 1 to 1. And then you do this at room temperature. That's what the little RT right here, or 80. You can see the conditions right here. And the reason it says room temperature or 80 is more than likely there's more than one set of conditions, right? And the yields are 50 to 99% for these 1,3 conjugated dienes, right? And the diastereomers ratio 5 to 1 to greater than 20 to 1. So we're gonna look at all of the tables to look at the different reagents and to look at uh, the products and things like that. So let's go down to here. And I'm just going to kind of dissect this just to make it make sense. So what's the whole purpose of doing this reaction? Remember when we talked about synthesis, we said that synthesis had right, it was kind of two-pronged. It was method development. Right, so method development is one purpose of doing synthesis, and then the other purpose is to make natural products. So method development is basically taking an existing reaction and improving it, or doing coming up with some type of innovation to do it a different way. And then the natural products synthesis, it is what it says. You actually taking molecules found in nature and you are recreating them or synthesizing them under laboratory conditions. So you can do them at scale, increase the amount that you generate, so on and so forth. Right. So this will be an example of a method development. Right. And the reason we say that it's a method development is because the Wittig reaction already existed. Right. It's not a new reaction. It already existed. What they've done is taken the Wittig and innovated or enhanced it, done it a different way, increased the scope of the reaction or the reactants that you can use to make alkenes, right? So here in the first sentence is that this is the innovation, right? Why do this version of the Wittig, right? Here's the innovation right here, right? To make conjugated dienes. That's a very important class of compounds, right? So this innovation gives a new method to make conjugated dienes, but is using an existing method, which is the Wittig reaction, right? So that's the whole purpose of doing the chemistry, right? Because you always want to know why somebody did something. Why did they do this and not something else? Well, the reason is that, again, this is another tool added to the synthetic toolbox. So it's another way to make conjugated dienes. And we've already talked about conjugated dienes, and you can see here the first reaction that they reference right here is the Diels-Alder reaction, right? That's a very important reaction. You can build up these cyclic motifs really fast using the Diels-Alder, right? And look at the reasoning. Again, you always want to ask why it's important, right? So now if you look here, right, occurrence of that 1,3-diene motif shows up in different natural products, right? And these natural products have biological and medicinal properties. And then they even give a reference to that particular statement, right? They don't just they're not just pulling that out of their behind, right? They give a reference over here, and if you look at the reference, it's in a journal called Accounts of Chemical Research, right? So Accounts of Chemical Research publish review articles, right? And so this review, I didn't pull it, but this review is more than likely dealing with the existence of that 1,3-diene in natural products that have biological activity, right? Everything has a, well, it's supposed to. Everything should have a purpose behind it. And so that's the purpose of uh, publishing this work. That's the intellectual merit behind the work, because you always want to, are you adding to the body of scientific knowledge that already exists? And yes, right? So let's look at and this is an example of what you call a communication. Right? You have, when you publish a paper in chemistry, you're either going to publish a communication or you're going to publish a full paper. Communications can be anywhere, for depending on what journal you publish in, 2 to 4 pages. A full paper might be 10 to 15 pages. All right. So let's look down here, and this is the rationale, right, behind, for the proposed mechanism behind what happens. We talked about the Wittig reaction, and we know that the Wittig reaction requires an illet, right? It goes through an illet. And so the question is, how does this go? How does this illet formed here, right? And so this is the proposed illet, and we're going to talk about this in a minute. But this is the proposed illet here, right? Or if you write it a different way, you can write it like this, right? So that when you see this, that little negative sign with a dotted arc over it, what that means is that that charge is spread out over those 3 atoms. It's another way to indicate allylic resonance, right? So that's the purpose of, so that indicates allylic resonance, right? And so that's probably why they chose this allylic system, because you can get resonance and stabilize that negative charge. All right, so I wanted to talk about that because it's kind of interesting uh, that the illet actually looks like that, but I'm gonna come back to it. All right, so up here is the first example, right? So they take this ester, allylic ester, right? And this leaving group right here is very important because that is the key to forming the illet. And I'm gonna show you why I believe that in a second, because I kind of went through this and thought about the mechanism for illet formation. So I'm gonna show you that in a second. But that's part of the reason why you can actually make the illet. All right. So you take triphenylphosphine, your aldehyde, you do this in THF, which is a pretty good solvent at room temperature, 24 hours, and you get 73% yield for the EE isomer. Notice right here, this is E, and that double bond is also, that's trans, right? The other double bond is E because it's tri-substituted, this one. And the other one is trans, but E and trans kind of are kind of synonymous. It just depends on the type of double bond you're dealing with. But we'll talk about that too. All right, so that's a great example of using existing chemistry and innovating with it. So let's talk about that. I want to take a snapshot of this, and we're going to talk about the mechanism for illet formation. page. Anybody have any questions so far? Right. And again, the whole point of this is to just kind of make it clear that this stuff is not just pie in the sky. Like, it's real chemistry, and people do this every day. Oh man, hold on. All right. All right. So let's think about this. So let me just redraw the starting material. And the block right here, I know you may be wondering what that is. It's actually a protecting group. It's what we call a protecting group. What it does is it keeps that oxygen from reacting. All right. So that's that. And then here is the allylic part of that. All right. So let's use what we know already. I know this is a kind of a complicated example, but we know enough that we can come up with something on this mechanism. All right. So let me ask this question, and let me show you what we're trying to get to. Right, because the illet actually ends up looking like this, and then maybe we can work backwards to see what happened. So that's that, and then this is the illet. That's what's going to react with your aldehyde. So how do we get there? What do you think happened? Look at the carbon. This carbon right here is the same as this carbon here. So how do you think phosphorus reacted? What do you think happened?
It attacked that carbon.
It attacked that carbon. Okay, let's do that. Let's show that. Good. So I'm going to attack here. Boom, like that. What else has to happen? That carbon has a pi bond to it. Is that correct?
Yeah, it's gonna break.
All right.
Should
So I'm going to push that here. And can you see how that is responsible for putting that double bond over here? Right. Now, what else has to happen?
The OPOP group has to leave.
Yeah, I have to get rid of the oxygen. And the fact that it has a Bach protecting group on it makes it a better leaving group too. Right. So that's going to get me to, actually, let me not do that. That's going to get me to here. I'll just redraw it. All right. Now, how do I get to here, which I could also write like this? I'm just gonna write the phosphorus part. Right. You know, I can also write the illet like that. So how can I pull off one of these protons? What do you think? Now I'm gonna put this plus that.
What did you do to the right? Did you slice off something?
Say that again.
On the right.
Which
The cleavage or something?
you mean right here?
Yeah, right under the final product.
Yeah. So I'm showing that the illet can also be written this way. Right? Because isn't the illet, let me do this. Didn't our other illet when we were studying this look like this?
Mm-hmm.
Is that right?
Mm-hmm.
Let me fix that negative sign. Or I could write it like that. Right?
Mm-hmm.
So that's what I'm showing down here. Right? The illet I have up here I can also show it like that with electrons.
Oh, you're showing how that it got the double bond.
Mm-hmm. Mm-hmm.
Gotcha.
I can put that arrow in here, and that'll put that double bond in there. So what that means though is that carbon right here, I need to deprotonate it. Is that right?
Yes.
In order to get to here, and eventually to the illet. Well, it's eventually to the other conformation of the illet. So what can I do?
Get rid of one of the oxygens. Get rid of one of the hydrogens.
Okay, I agree with that. How?
I think I heard somebody say use the oxygen.
That's right. We have that. We lost that Bach group, O-Bach group in the elimination part. So boom, we can just come back here and do that. Right? And that'll get us to, let me do this. This version of the illet, which would eventually get me to this version of the illet. All right. So even though we don't know like all the ins and outs of this chemistry, there's still pieces of it that we know, because at the end of the day, every reaction is going to come down to nucleophiles and electrophiles and acids and bases. And that's all this is nucleophile, electrophile chemistry. Up here, the nucleophile is here, right? And this is my electrophile. Is that right?
Mm-hmm.
All right. And then down here, this is base. And then this is acid. Right. And then when I react the illet with the aldehyde, the illet itself becomes the nucleophile and the aldehyde becomes the electrophile. So all this is, everything can be broken down or boiled down to nucleophiles and electrophiles and acids and bases. Everything. What I'm trying to show you is that it's not esoteric. Like, oh my gosh, this is so ethereal. I don't have no idea what to do with this. But yeah, it's really all comes down. If you understand nucleophiles and electrophiles and sources and sinks and how they interact with each other, then you can look at anything and kind of come up with a mechanism. All right. So let's go back to here. Right. So if you look at the substrate 1, right? What you'll notice is that, and what you're going to notice in this paper is that they kind of switch up different, they test different perturbations, right? Here, they tested what happens with X. What if I make X a methoxy group? And you see that the results are down here. If X is methoxy, the reaction doesn't work. If X is an acetate, they get 82% yield with a 3-to-1 ratio of EE to EZ, right? And you see these, you can see here, see how they have these little bonds, kind of squiggly, undefined. It means it can be up or down, right? So it can be, the product can look like this. Right, that's a potential product, or it can look like this. All right, so we can make that pen a little bit thinner. Sorry. All right, so that those double bonds, they have them undefined for a reason, because you can get more than one product. Right. So again, they're testing different elements of this reaction, or different components of the reaction. So they tested to see what we can make X. So X as an acetate works, methoxy doesn't work. So then you'll see in the next, and this is all again testing the scope of the reaction, right? And so what it looks like is that X needs to be electron withdrawing, right? Because methoxy is electron rich, and then the acetate is electron poor. This is OAC, and this is OMe. Right, so all that stuff matters. That's going to have an electronic effect on the reaction, right? And one of the parts that we just saw in the mechanism was that you need to eliminate the alkoxy group. So OAC is going to be a better leaving group than methoxy when you do that elimination, right? The pKa of the conjugate acid here, 4.6. pKa, the conjugate acid for the methoxy, by 17. Right? We learned that already. Am I right? About how you can tell which leaving group is better based on the pKa of the conjugate acid. Didn't we do that when we were doing substitution and elimination? Okay. Yeah. So you can see again, those basic concepts never go away. Even when you're doing complicated chemistry, the basics, you never forget the basics. You can never get away from the basics. All right, let's go to the next table and see what they did here. Right, so here is, again, they optimize and this is all of what they call optimization. Find the best leaving group. Now they want to find the best aldehyde, right? So here, the Bach leaving group is there, but now they're changing up the aldehyde. And that's the standard method development. You test every part to see what the optimal functional group is for that particular species. You test everything. So you test the leaving group. Now they're testing the aldehyde, and you can look down here, and you can see they did a bunch of aromatic aldehydes. They did a bunch of nitro substituted aromatic rings, so on and so forth. Look at the scope. Look how many aldehydes they tested, right? And then they also tested this R1 group. So they're changing this group and they're changing the substituent on the aldehyde at the same time, right? So notice in the table for R1, they did 15 trials or 15 different reactions, right? Where they left R1 as just a aromatic ring. But then they varied the aromatic ring attached to the aldehyde. And then they even did some aliphatic aldehydes as well, right? Aliphatic meaning simply there's no double bonds present. All right. So all of these different perturbations, what they're trying to determine is the best set of conditions to do this reaction under, right? And then you go further down the chart, you can see now they varied the right, they switched up again. Instead of just using an aromatic benzene ring, now they put a chlorine on, or a nitro group, or a methoxy group, so on and so forth. Again, you're testing the electronics. The nitro group is electron withdrawing, so that's going to be an electron poor. The chlorine and the methoxy on an aromatic ring are both donors. We talked about that before, right? With the aromatics, how the chlorine is a donor, and then the nitro group or any type of electron withdrawing group is going to be an acceptor when you attach it to that aromatic ring. All right. Any questions? Look at the results, right? Based on these results, right here you got 99% yield and 10-to-1 stereochemistry. And let me see what the stereochemistry is. It says C. Where's C? Oh, EE. So the major product is EE, where both of those groups are trans, basically. All right, so you get 10-to-1, 99% yield. Right here, you get greater than 20-to-1, 97% yield. And that's with a meta-nitro benzaldehyde, and let's look at the other. So here. So we can illustrate that. Let me see if I can find some room to do that. So that is, so for R right here, for that reaction, that's 97% yield and 20-to-1. Let me see. What can I do? Uh-oh. That's too big. Sorry. So you're taking so that's your star material, one of them. And then your aldehyde is meta-nitro benzaldehyde. So your aldehyde is going to look like this. Right, so that's that set of reagents gives you a 97% yield and greater than 20-to-1 ratio of stereoisomers. Right, so R2 over here is going to be here. And then, of course, R1 is the benzene, just a plain benzene ring. All right, so that's just gives you an idea of the type of functionality that you can incorporate in these. That's a huge scope of reaction, by the way. They got 25 different perturbations, and all of them give you pretty decent yields too, and good selectivity. So that makes this reaction pretty valuable because you can do a lot of different types of substrates. You can do electron rich or electron poor substrates, and you get good stereochemistry. Uh, so yeah, that makes this reaction very appealing. All right. Any questions? So again, if you look over here, so what have they optimized up to this point? They've optimized the leaving group, the OBOC, right? That's the best leaving group. They found that the best aldehyde is para-nitrophenyl benzaldehyde. So with the nitro at the para position. And then they also are looking at R1 being nitrophenyl. Let's go over here and look at what that gave. Is that metal? Yeah, metal. I don't see a metal in the chart for the starting material. Interesting. And we see the metal up here, but not on the substrate side. That's okay. All right. But in that reaction, where you put a nitro group on both sides, you get a greater than 20 to 1 stereoisomer ratio and 95% yield. And it's at room temperature, right, for 1 hour. Now that is what you want from a reaction. Short reaction time, and room temperature. So no special conditions, no heating, no cooling, nothing like that. So that again, that's another desirable characteristic of a reaction. Be able to do it at room temperature and do it for a short period of time and get high yield and high selectivity. Right? That's the goal of every single chemical process that anyone has ever done. Low reaction time, we'll do it at room temperature, and preferably the only other part of this that I would tweak or try to tweak would be the solvent. Right? It's done in toluene, and toluene is a pretty sucky solvent. It takes a lot to get rid of it at the end of the reaction. All right. Any questions about anything? And down here, they just showing the transition state for why they see the selectivity, right? Why is it always EE? Right. So you can see in one transition state over here, the one that says unfavored. And this is standard too for the Wittig, that it goes through this kind of like puckered transition state. So you can see over here, this little symbol here means that there's some steric hindrance between the electron withdrawing group and R2, right? So that's going to disfavor that transition state and favor the other transition state on the right, where R2, now you see R2 is pointed down away from the electron withdrawing group, right? So that alleviates that steric strain. All right. Any questions? All right. So that's again, that's just another application of some of the reactions that we've been looking at, like the video. There's another paper. It's not. I didn't get the full paper because I couldn't access. We didn't have access to it. But this is an example of, and this is published in the journal Synthesis. It's a European journal, a highly reputable journal. But this particular reaction is a modified version of the Gabriel synthesis, right? You can see right here, you have phthalimide, and then over here, it's done under some different conditions, but you have DIED and triphenylphosphine, 4 hours, and THF at room temperature. Notice though, over here, you don't have an alkyl halide. You actually start with an alcohol. All right, but the process, the overall process is still the same. You're going to convert that alcohol to a beta leaving group and then attack this carbon right here with the nitrogen from the phthalimide. All right, so that's all of that is it's just a modified version of it. And then this is your product. But this is the product before releasing the actual amine, right? Because this part right here is still, the phthalimide is still attached. And you have to treat it with base in order to open that ring up, open that phthalimide ring up and release the amine, right? But look at the different substrates, right? You can actually make this amine in 93% yield, right? Or you can make this amine, right? That would basically be starting from I think that's menthol. You're basically starting from menthol and converting menthol into an amine. You can do it 98% yield, room temperature, and THF at 4 hours for 4 hours. That's pretty amazing. But this is it's a menthol derivative. I'm sorry. All right, so same here. 76% yield, and the only problem here is the stereochemistry is not defined, so we don't know if it's R or S, right? But still, to get that amine with that functionality and that the stereochemistry already set and 76% yield, that's a good reaction. All right. Any questions? So I think it's always important to see some application, right? We can talk about these reactions, but the application part is important too, because you need to know that this is real stuff that happens in real places, and it's not just on paper. All right. Any questions? Anybody got any questions? No. All right. I'm gonna stop there. Remember tomorrow we don't have a class. We won't log in. You'll just take the exam. I gotta finish writing it too. But it'll be up by class time tomorrow.
So you saying we don't have class Friday? We just take the exam.
Mm-hmm. That's what I meant. Friday, not tomorrow.
Also, can I ask you a question about Organic Chem 1 lab?
Sure.
What is the final composed of?
For Organic 1 lab,
Mm-hmm.
it's just different questions about aspirin synthesis.
Okay.
And a couple of NMR questions on there. But for the most part, it's mainly just dealing with aspirin synthesis.
Okay.
Yep.
Are we going to have class on Monday, Dr.
Yeah.
Russell?
Yes. Monday is the last day of class. Am I right? No, Tuesday. Well, Monday is our last day.
Yes.
Tuesday is the 10th. What's the 10th?
No, the 16th is the last day, I believe.
The 17th or the 19th?
16th, I think.
The 17th is the last day of classes.
Yeah. So,
never mind.
And
Monday,
the 21st is the last day of finals.
Yeah, Monday will be our last day of class. So what we'll do on Monday is probably review. I may pull up the exams and go over the exams. because I'm not going to start like another lecture teaching another topic. But I'll probably pull up Blackboard, pull up the exams, and we can walk through something like that. So yeah, but no class on Friday.
Okay.